So let's start. Okay. Uh, Already in the earlier class, we have discussed something on current deficiency, current excess. Again, I should tell you that what is current current deficiency, current excess. Again, current deficiency uh, is the actually it occurs when a train travels around a car at a speed higher than the equilibrium speed. Basically, it is the difference between the theoretical current required for higher speed. Suppose uh, actual train is running with high speed. Listen, this current deficiency. Train is running with high speed, and whatever the super elevation or current has been provided on that curve, this difference value, the train is running some higher speed, and for that speed whatever the super elevation required, this value, the difference between this value and uh, deducted, we can deduct the actual provided value of which is provided on the curve. Suppose some super elevation value has been provided on the curve, but for that super elevation value our train speed is 60. Suppose some super elevation value or some current value has been provided on the curve, and on the basis of that super elevation our train can go with suppose 60 kilometer per hour. But actually on that curve or on that track our train is running 80 kilometer per hour. So for 80 kilometer per hour super elevation required another, and for 60 kilometer per hour super elevation value is different. For 80 kilometer per hour super elevation value is different. For 60 kilometer per hour super elevation is different. But on the track actually provided super elevation for 60 kilometer per hour. This difference of super elevation value is actually the current deficiency. Same as suppose your super elevation has been provided on the track for 80 kilometer per hour, some value which is actually practically provided or actually fitted on the curve in the track, but your train is running with 60 kilometer per hour. Average speed of the train is 60 kilometer per hour. So for 80 kilometer per hour the super elevation value is 1, but 60 kilometer per hour is different. Both the value is different, but there is showing some difference because you have provided something and your train is going with some speed. So you have provided some value. For current deficiency you have provided low super elevation value for lower speed, but your train is going with high speed. And for current excess condition you are provided higher value, the super elevation for higher speed, but your train is running with low speed. These super elevation value difference, practical and theoretical. Practical, which is provided super elevation you have provided in the field, and which is actually theoretical, which is you are calculating for your train, actually practical, which is happening. These difference value, this is current deficiency and current excess. Current deficiency, which is you have provided low super elevation value, and current excess is the you provided higher super elevation value or current value, but your train is going with low speed. What is the significance of current deficiency and current excess? You can understand today. This is the most important thing in your calculation or to find out the permissible speed of the train, actual which speed we should we should provide for our particular track for from these two conditions, current deficiency condition and current excess condition, we can calculate. Okay, both are the design parameter for calculating permissible speed of the train on car. So we are coming this current deficiency and current excess. Before that, we have new thing in railway engineering, that is negative super elevation. Okay, negative super elevation, this is only used for railway. Super elevation we know, can't, or super elevation we know what is super elevation, but negative super elevation, it is only possible in railway track. Okay, negative super elevation, most important thing, very critical question, and it is only this question is available for railway engineering. Negative super elevation, when the main line lies on a curve and has main line lies on a curve and has a turnout of bookish language, that is contraflexure. Okay, opposite flexure from the main line. This is main line and opposite flexure from the main line. Okay, this is contraflexure. This is called contraflexure. So when the main line is main lines on a curve and has a turnout of contraflexure leading to a branch line. This is branch line. This is contraflexure, opposite flexure. So leading to a branch line, the super elevation is necessary for average speed of trains running over the main line curve cannot be provided. So when train is going through this main line, so somewhere this A to P, that position, some super elevation is required, because this is the curved section. This is the A to B, this is the curved section of main line, and super elevation at least super elevation required at A to P, at this position super elevation is required to provide a comfort of the journey. Okay, or to prevent the accident of the train. A to P, or suppose A to B, we need the super elevation. Without super elevation we cannot handle, normally in normal condition we cannot handle the train journey, or we cannot provide the comfort to the passengers, or it is better if we provide the super elevation at the main line. Suppose A to B, one of the track of the main line A to B, we should provide one super elevation. But at the same time you can see the branch line is there, one branch line, and bookish language is contraflexure. Okay, contraflexure or opposite flexure turnout, which is present at the same position. How can we provide the super elevation? Because also branch line it need the super elevation. Suppose where it suppose CF, CP or CF, whatever, one of the track of the branch line, outer track of the branch line, also this branch line need the super elevation. So when I am providing super elevation on main line, suppose A to B, one of the track of main line, outer track of the main line, I am providing super elevation. So at the same time, how can I provide the super elevation on branch line also same time? This is called the big problem in railway. Okay, for that purpose negative super elevation has been invented. Some speed restrictions, some numericals are they are offering some numerical on the basis of this negative super elevation condition, or that kind of situation. For that kind of situation they have provided numerical. So now railway has introduced for that this kind of situation negative super elevation condition. Negative super elevation, what is negative super elevation? Again I am repeating the same thing. When the main line is lies on a curve and has a turnout of contraflexure leading to a branch line, the super elevation is necessary for average speed of trains running over the main line curve cannot be provided. Okay, so in the main line super elevation normally not provided. Actually it is not provided, the super elevation for main line, but some speed is necessary for main line. For restriction speed is there to passing through this main line. In this figure, which is outer rail of the main line curve must be higher than CD. Okay, for the branch line, however, CF should be higher than AE or point C. CF should be higher than for branch line, and for main line CD should be higher than AB should be higher than CD, and these two contradictory conditions cannot be met within the layout. In such cases, the branch line curve has a negative super elevation. Okay, in that case the branch line curve has a negative super elevation, and therefore speeds on both tracks must be restricted, particularly on the branch line. Okay, so speeds not only branch line, also main line also, so speed should be restricted for these cases. Speed on the branch line and speed also in the main line. Okay, speed should be restricted, and some negative super elevations situations or negative super elevation has provided for branch line, and no super elevation is provided for main line. But the situation, what should be the negative super elevation, or what should be the value of branch line, we are coming with some numerical, then it will be clear to us. So the provision of negative super elevation for the branch line and the reduction speed over the main line can be calculated by some methods. So first, the equilibrium super elevation for the branch line curve is first calculated, and this is the formula. Equilibrium super elevation is the actual speed, equilibrium speed or average speed, which is actually maintained on the track, that is equilibrium speed, and for that equilibrium speed we can calculate the equilibrium super elevation. Okay, equilibrium speed is the balance speed, no harm for the train as well as track. This is the equilibrium speed, and for that equilibrium speed we can calculate the equilibrium super elevation. The equilibrium super elevation formula is simple, same formula earlier I have discussed. The E equals to GV square by 127 R. Okay. Number 2, the equilibrium super elevation E, small e, is reduced by the permissible current deficiency CD, permissible current deficiency, and the resultant super elevation to be provided is, suppose X is the resultant super elevation, E is the equilibrium super elevation, and CD is the current deficiency. Okay, current deficiency is, what is current deficiency? When your train is running with high speed, but you have provided the less super elevation, whatever required for the actual speed, but you have not provided. This is called the current deficiency or current super elevation. Okay, super elevation deficiency or current deficiency. So resultant super elevation is required. Resultant super elevation equals to E minus CD. E is the equilibrium super elevation, the balanced or for equilibrium speed, the super elevation is called equilibrium super elevation. So equilibrium super elevation minus Kant deficiency for the particular curve, and Kant deficiency is the difference between the train is running with high speed, Kant for the train with running with high speed minus the Kant provided on the track. This is the Kant deficiency value. Third, the maximum permissible speed on the main line, which has a super elevation of x. The maximum permissible speed on the main line, which has a super elevation of x, is then calculated by adding the allowable Kant deficiency x plus cd. The safe speed also calculated, and the smaller of the two values is taken as the maximum permissible speed on the mainline curve. So maximum, this value is required, x value is first can be calculated from this E minus CD. After calculation of this x value, the maximum permissible speed on the main line to be calculated. Okay, maximum permissible speed is needed for main line, which has a super elevation of x, is then calculated by adding the allowable Kant deficiency. Kant deficiency normally in case of super elevation always negative. Okay, always negative, and the safe speed is also calculated, and the smaller of the two values is taken as the maximum permissible speed on the mainline curve. This also will be clear in numerical. And after that, we need to find out the safe speed on curves. Okay, safe speed on the curve. Acha, before that, something is required, that is allowable Kant deficiency. We know the Kant deficiency and Kant excess or super elevation deficiency or super elevation excess. What should be the value of Kant deficiency? Normally, we can take the Kant deficiency value as 75. Sometimes we can take 100. This is the table where lots of things are written, but my suggestion for solving numerical, we can take 75 or 100 for Kant deficiency. Okay, for Kant deficiency, strictly we can take 75 or 100 for calculation. In numerical also it will be clear. And for Kant excess, the limiting values of Kant excess have also been prescribed. Kant excess should not be more than 75 on broad gauge and 65 on meter gauge for all types of rolling stock. So Kant excess value also 75. In numerical, my suggestion, you can take Kant deficiency 100 and Kant, because sometimes you can see that this value can excess or maybe greater than 100. So at that time you should take 100 value also. Okay, and this is also, you can see sometime greater than 75, you should do at that time 75 only. So this is the limiting value for Kant deficiency and Kant excess. And after that, this safe speed on curves, it is required. For all practical purpose, safe speed refers to a speed which protects a carriage for the from the danger of overturning and derailment and provides a certain margin of safety. Earlier it was calculated by applying Martin's formula. Lots of formula were there in earlier cases, but after modification, 2 or 3 modification, the final formula, new formula which is available to us, and earlier Martin's formula was used to work out the maximum permissible speed or safe speed on cars. This empirical formula has been changed by applying Martin's formula was based on empirical condition, and after Martin's formula or empirical formula has been changed by applying a formula based on theoretical consideration as per the recommendation of the committee of directors, chief engineers. The maximum speed for transitioned cars is now determined as per the revised formula, and these are the formulas. Suppose this for the broad gauge, this for meter gauge, this for narrow gauge. For broad gauge, this is very important formula. This formula V equals to root over CA plus CD into R by 13.76. Okay, this CA, what is CA? CA is the your actual current of the curve, actual current which is provided on the curve. CD is the deficiency, current deficiency. R is the radius of the curve, and 13.76 is the constant value. And through this formula, we can calculate the safe speed on the cars. We in this railway engineering, as a numerical, there are lots of design for numericals. So for design calculation, first we have to calculate the super elevation value for my track, or what should be the super elevation value on the curve section. And another is also with super elevation, speed of the train is necessary to find out. So one is super elevation is needed, another is speed of the train. Both the things are important for designing. uh, Suppose this formula where V is the maximum speed. In kilometer per hour. CA is the actual current in millimeters. CD is the permitted current deficiency in millimeters. R is the radius of millimeters. Achha. Okay, and for meter gauge, V equals to 0.347 root over CA plus CD into R. So same thing, CA is the current in actual current in millimeters. CD is the current deficiency in millimeters. And this for narrow gauge, 762 millimeter narrow gauge. Okay, V equals to 3.65 root over R minus 6, subject to maximum of 50 km per hour. But these two things are necessary. Actually, problem will come from this based on these two problem for broad gauge and for meter gauge. Okay, we have one numerical. Please write numerical. Do you have copy? Hello.
Yes, sir.
Please write this numerical. You have to send me a picture in my mail. Please write this numerical. Calculate the super elevation and maximum permissible speed for a 2-degree broad gauge transitioned curve on a high speed route with a maximum sanctioned speed of 110 km per hour. The speed for calculating the equilibrium super elevation as decided by the chief engineer is 80 km per hour, and the booked speed of goods train is 50 km per hour. Please write this problem. Numerical. See solution. Have you written? You have to send me the picture of the huh? Hello, Dipesh?
Sir, wait 5 minutes only.
Okay. Please write this numerical. You have to send, all of you send me this numerical. This is the assignment, one of the assignment, class assignment.
Sir, written, sir.
Please write, because you have to send me in my mail. Okay, this is one of the assignment. So again, I am repeating the question. Calculate the super elevation. With question, please. With question, send me with question. Okay. So question is the calculate the super elevation and maximum permissible speed. Super elevation and maximum permissible speed for a 2-degree broad gauge transitioned curve. Okay. So a curve which have the degree is which have the 2 degree, and you have to calculate the super elevation and maximum permissible speed for that curve. Okay. So a high speed route with maximum sanctioned speed for the route is 110 km per hour. Sanctioned by some engineer, that is 110 km per hour for the route, which have the degree is degree of the curve is 2 degree. The speed for calculating the equilibrium super elevation as decided by chief engineer. The speed for calculating the equilibrium super elevation as decided by chief engineer is 80 km per hour. This equilibrium super elevation, that is this is the equilibrium speed. This speed is for equilibrium speed. This super elevation for this is the equilibrium speed, and the speed for calculating equilibrium super elevation as decided by the chief engineer is 80 km per hour. Okay, this is the super equilibrium speed, and the booked speed for goods train. For goods train, always speed should be low, and for that track, for that car, the speed for good trains is 50 km per hour. Okay, this is equilibrium speed. This is speed for good trains. Therefore, this is the low speed. This is required for your current excess, and this is your higher speed 110 km. This is required for your current deficiency. Okay, this is required for your current deficiency, this 110 km per hour, and this 50 km per hour required for your current excess. Okay, now see the solution. Solution first, please start to write down solution. R, first calculate the R value, the radius of the curvature. Simple formula 1750 by d. D is the degree of curve, 1750 is the constant for calculating R value. So your R is 875 meter. Okay. Next, the super elevation for equilibrium speed. Super elevation formula is same for all the cases. Just we have defined suppose for low speed, for medium speed, for equilibrium speed, for high speed, for restriction speed, but super elevation formula is always same for railway. GV square by 127 R, where G is 1750. Already mentioned in the last classes. G value is for broad gauge 1750. Okay. GV square by 127 R. Simple. Now we are calculating super elevation for equilibrium speed. Equilibrium speed means equilibrium speed. Equilibrium speed is in question. It was given that is 80 km per hour. Okay. So V should be 80 km per hour, and R already calculated. R value is always same. R value is always same. Just wait. आशीष थोड़ा देर बात कर सकते हो, क्लास चल रहा है. So super G is 1750, V is 80 km per hour, and R is 875 meter. R is same for all the cases for this question. Now super elevation should be 1750 into 80 square by 127 into 875. There is super elevation for equilibrium speed is 100.8 mm. Please write these things.